Welcome back everyone to Chapter 12, Section 1. In this video we're going to upgrade, right? Last time we talked a little bit about sketching points. Now we're going to talk about sketching full-on surfaces. So yes, we're going to sketch not maybe the really extreme ones quite yet. We're going to do relatively simple surfaces. And then we also want to be able to identify, right, when a point lies on, some specified surface. So let's get to this, kind of a bit of a review with our algebra days back here. All right, so we have one objective down. The claim is this is going to be our strategy for identifying whether a point is on a surface or not. Now let's go ahead and start working towards sketching some of these surfaces on our own here. So I'd like to again kind of start off with our two-dimensional, right, kind of back in our algebra days, and see kind of how can we extend this to the three-dimensional case here. So I want to graph the equation y equals 1 on the xy plane and then describe it in words as best as possible. So nowadays we're pretty good about just looking at y equals 1. You could probably say, well, it's going to be a line, the slope is 0, the intercept's 1, right, and you really don't need to do any work. But I want to kind of revert back to, again, we're trying to build up this three-dimensional sense, so I'm going to kind of stop and think about what did we do originally when we first came across this equation. How did we maybe graph this thing? So let me go ahead and I'm going to draw my xy plane here. So here's x and here's y, and okay, the y equals 1. So probably the first way that we graphed basically every single equation that you've ever come across is that you use the point plotting method, right? You would choose different values of x, then you would feed it to your equation and see what happens, right? What was the output? What was the y value that came out of this? And so this one's kind of relatively boring, right? So I mean, if I take x equals 0, for instance, so x equals 0 would be right there on the y-axis. And if I fed that to my equation, you notice that there's no place to stick x. And so it just outputs y equals 1. So y equals 1 would be up here, so I'd get the point 0, 1. And then if I wanted to input the value x equals 1, so over here, and then, well, again, the equation really doesn't care about x whatsoever. It just says, well, y equals 1. So no matter what x value you feed to this thing, whether it be 2 or 3 or 4 or negative anything, right, all of them output y equals 1. And when you combine all of these points, right, because it's not just at the integers, you could also do x equals a half or x equals a third or anything like this, right? But it's when you combine all of these points that satisfy this equation, you get this nice horizontal line right here. So that's why, when you graph this, you get a line, a nice horizontal line. All right, so I've already said this, but let's write down, right, we get a horizontal line and horizontal kind of tells you already about the slope. So I'll also mention that the y-intercept, which I'll just go ahead and denote y-int, so y-intercept of 1. All right, and one last thing to think about before we move on to the next part where we're going to upgrade and actually do this in 3 dimensions is that I'd like you to think of equations here as almost restrictions. So equations and restrictions are kind of the same thing. So notice that this didn't have any equation or any restriction on x. X could be anything it wanted. But y had to be 1, right? So x could kind of roam free, back and forth here, left and right, and there were no restrictions on x. But y couldn't move up and down. Y had to be equal to 1. So to some extent, thinking about this as a restriction ends up being a really useful idea, especially as we move forward. All right, well then, let's go ahead and do the same sort of thing here. Graph the equation y equals 1, but now we're not in the xy plane, right? We brought up last time that this means the xyz space. So let me go ahead and maybe draw out my axes here. So this is going to be maybe my x-axis. Here we're going to have a y-axis, and here we're going to have our z-axis. And I'd like to graph this y equals 1 now in 3 dimensions. And again, I'd like to invite you to pause the video here if you'd like and try this on your own, and then we'll go ahead and go over it together. All right, so just as before, right, y equals 1 is a restriction. Notice that there are no restrictions on x, and there's also no restrictions on z. They can be anything that they want, but y has to be equal to 1. And so just like before, we use the point plotting method to go ahead and get this line probably the first time around. We're going to choose the point plotting method again to try to get whatever this surface looks like. So for instance, if I chose x equals 0, so I'm not moving out at all, So x equals 0, z equals 0. That's probably also good. So I'm not moving up and down whatsoever. And then y would have to be 1. So I'm going to have to move out to y equals 1, and I'm going to put a point right there. So that is 1 point that would lie on this surface. Now, there are still no restrictions on x. So for instance, if I made x equals 1, and for the time being, let's use z equals 0, again, y would still have to be equal to 1. So I'd kind of go out here. There we go. X could be 2, or x could be 3, right? And still, y would have to be 1. And I'm just choosing z equals 0 for the time being. We could also go in this backwards direction. But the big thing is that y always has to be equal to 1. So this is me kind of roaming free in the x direction to some extent, right? There are no restrictions on x. I can go back and forth in my x direction. In this case, I'm choosing z equals 0. But you could say, well, let's also roam free in kind of our z direction, right? Z can be whatever it wants. There's no restrictions on z. So maybe if I let x be equal to 0 for the time being, and I do z equals 1, so I move that up, right? So again, y has to be equal to 1, so I have to go out 1 in the y direction. But z could be equal to 2, and I could go out in the 1 in the y direction. Or z could be equal to 3, again going out 1 in the y direction. I could also go down, something like this. Right? And you could also do any combination of these things, right? I just happen to be choosing either x or z to be equal to 0, but for instance, I could choose x equals 1 and z equals 1, and notice y would also have to be 1. So I could go out 1 in the x direction, up 1 in the z direction, and the only thing that has to remain true is that y has to be equal to 1. So I have to go out to y equals 1. And so it's kind of, again, the combination of all of these points, I guess more formally, right, the union of all of these points, just like before they made, oops, that kind of went very fast, before they made this line, right? When you started connecting all of these things together, you made a line. In this case, the claim is we're going to make a straight up and down sheet of paper sort of deal where y is equal to 1 all of the time. So again, we could do kind of in this backwards direction, kind of any of these, even in between these points here, right? So long as y equals 1, this right here is going to be the surface where y is equal to 1. So this right here will give us a nice vertical plane. Vertical plane. And you may remember in our last video, we actually graphed y equals 0, and that was the xz plane. And actually before this video, I went ahead and I graphed this one, y equals 1. So again, I'm over here in this Monroe 3D Calc plotter, and I graphed y equals 1. And you can see you get this plane, and kind of there's all of these lines that are being connected together. And this is, again, quite nice because you can go ahead and rotate it and see. Again, x and z can be whatever they want, but y has to be equal to 1. And so that's why you get this nice vertical plane here. All right, so, oops, meant to click this one. That's kind of a relatively nice scenario here. Let's go ahead and try the same sort of thing one more time, but we're going to go ahead and change the equation on us a little bit. Instead of just y equals 1, we're going to have x squared plus y squared equals 4. First, we're going to graph this in the xy plane just to kind of get a nice running start here. And then we're going to go ahead and try to graph the same thing in xyz space. So again, you can notice that there's some trend here, right? I would recommend that you pause the video and try this. See how far you can get, and then I'll go ahead and go over it with you. All right. Every once in a while, I like to do a little bit of, video editing magic sort of deal. So I went ahead and I graphed this equation here. You can use the point plotting method like we did the last time, or there's some of you who may look at this and remember back from our algebra days, right? This whole x squared plus y squared equals r squared sort of deal. This is an equation of a circle centered at the origin. So this is a circle. And whenever you're trying to describe it in words as best as possible, for a circle you usually specify the radius and you specify what's the center. So circle centered at the origin, so in this case 0, 0, with radius 2. So again, this whole r squared, in this case, our radius would have to be 2, because 2 squared would be 4 in this case. And we don't allow for negative radiuses typically. All right, so that is kind of the warm-up problem. Now we'd like to go ahead and graph this in 3 dimensions. Again, that's kind of our main goal here for this video or this class, right? So I want to graph x squared plus y squared equals 4 now in 3 dimensions. Well, you can notice that this equation here has restrictions on x and y, right? X and y can't be any old thing they want to be, but z can, right? There are no restrictions on z whatsoever. So maybe the first thing you do will say, well, what if I did z equals 0? So z equals 0, well, that's the same thing as the xy plane, right? That's just saying that we're not moving up any, we're not moving down any, we're just staying at height 0, aka in our xy plane. If I go ahead and maybe just outline that there. And in fact, we already graphed this equation, x squared plus y squared, in our xy plane. So we could go ahead and do that same thing here, right? So I could move out 2 in the x direction, 2 up, 2 down, I guess in the, in the positive y direction, in the negative y direction. And I could also move 2 in the negative x direction. And if I kind of put all these things together for my z equals 0, again, I get my circle, but now it's just kind of in this xy plane. It kind of looks flat, right? Because we just basically had a different vantage point over here. So that's when we have z is equal to 0. But what if instead I did z is equal to 1? Again, there are no restrictions on z. Z can be anything it wants to be. So if I do z equals 1, so now I'm going to go ahead and just move this up here, right, to z equals 1. So instead of 0, I have 1. But then the picture would remain the exact same, because notice that there's no place for me to plug in z. Again, z can be whatever it wants to be. And so this picture would end up being the exact same picture, but now just at a new height, at a new z value. So again, I could go maybe out 2 in the x direction, I could go in the negative x direction, I could go in the positive y direction, and I could go in the negative y direction. And again, I'd get the circle of radius 2, kind of centered around now this z-axis here, but now it's just been shifted up, right? Instead of z equals 0, it's around z equals 1. And you could say, well, can't you do that for any z value? Can't you do that for z equals 2? So if I went even higher, right, again, I would get the same picture, the circle. Or if I did z equals negative 1. That one's not my best work there. Maybe I'll go ahead and erase that and try one more time. There we go. Or z equals negative 2, or z equals negative 100, or z equals 1,000, or whatever, right? Any z value would work. And you're just basically dragging along these shadow circles up and down. And so in this case, this surface is going to be a nice infinite cylinder. I don't know why I chose yellow, but okay. So again, if I'm describing in words as best as possible, this is an infinite cylinder. Because, right, there are no restrictions on z. There's no top and bottom, right? It's just going to keep on going up and up and up forever, and down and down and down forever. And it's centered around the z-axis. So I'll say centered around z-axis. And so again, this fact that we didn't have any restrictions on z, this is what helped us kind of sketch this picture here, is that we knew that we just took that circle and we were allowed to drag it really in the z direction, because z could be anything. All right, so one more time here. This is our last problem for this video. Graph the equation z equals y squared, again in our 3-dimensional coordinate system with x's and y's and z's. So just as before, I would advise or recommend that you try pausing the video and try to get as far as you can on this one. Notice that in our last equation, right, that was missing the z, and we used that to our advantage to kind of sketch this picture. This one actually has a z, and it has a y, but it's missing an x. So the fact that it's missing an x, we're going to want to utilize this somehow, right, and help sketch this in the x, y, z space. So again, pause the video if you would, try it out, and then we'll go ahead and do this together. All right, so hopefully everyone who wanted to give this a go went ahead and did this. So the first thing I'm going to go ahead and sketch this in is I'm going to choose x equals 0, right? I gave the hint that because this picture doesn't have any x's in it, because the surface doesn't have any x's in it, that's what we're going to kind of use, just like last time when we didn't have any z's. We're going to go ahead and use the fact that we don't have any x's to help sketch this picture. So first I'm going to go ahead and try to sketch it when x would equal 0. And x equals 0, just as we talked last time, this is one of the coordinate planes. If x is equal to 0, this is where we have y's and z's, right? Again, x would be equal to 0. So again, kind of we're not moving out in the positive x direction at all. We're not moving in the negative x direction at all. We're right here at x equals 0, and that's the same thing as the yz plane. And this is really good for sketching this equation, right? Because we have y's and we have z's. So let's go ahead and sketch y squared equals z. So just as before, maybe the first time you came across any, kind of new equation like this one's a little bit peculiar because it has y's and z's in it. I go back and I use the point plotting method. So I'm going to choose, okay, what happens if y is equal to 0? So if I plug in y equals 0, well, 0 squared would give me out 0. So this is just going to give me a point here, 0, 0. And again, we're already in the x equals 0 plane, the yz plane. What happens if if y was equal to 1? So if y was equal to 1, again, if I go back and I plug this into my equation here, well, I'd get 1 squared. Well, okay, 1 squared also is 1, so this would be this point right here. What if y was equal to -1? So if I was to go backwards a little bit, and -1 squared, well, that is +1 as well. And so you may recognize this already. Maybe you don't even need to use the point plotting method at all, right? For those of you who recognize, this should be a parabola of some sort, right? We're very familiar with y is equal to x squared. That's kind of like the classic parabola. But now we've kind of switched things around, right? Because our dependent axis here is z, not y. So z, so that's kind of the bit going up and down. And then our independent variable here, our independent axis is y, right, over here. So our inputs are y's. So just like when we had the dependent variable y and the independent variable x, right, back from our algebra days, kind of that's why it draws the same picture here. But now we just have these things by different names, right? Instead of x's and y's, we have y's and z's. Oops, deleted a little bit too much. There we go. All right, so this is what it looks like in the x equals 0 or the yz plane. So let me go ahead and sketch this, right? So if I was to plug in y equals 0, I get z equals 0. If I was to plug in y equals 1, I'd have to get z equals 1, so it goes up like this. And if I was to plug in y equals -1, so going in this backwards direction, I would get z is also equal to 1. So I get something like this. And so we get this picture right here in my yz plane, and now I've just drawn it in the 3 dimensions here. And this would continue to go on forever. Okay, and just as before, we say, well, what was special about x is equal to 0? X can be whatever it wants to be. There are no restrictions on x for my equation here. So x could be equal to 1, or x could be equal to 2, or x could be equal to 3, or -1, or -5, or anything in between. And the claim is the picture would be the exact same in all of these situations, right? Because this equation doesn't depend on x, right? There's no place to plug x in. The picture doesn't change. So whether this is x equals 1 or x equals 2 or anything, x equals, right? You get the same picture. So, okay, let me do my best here to maybe sketch the same picture here, but just shifted in this x direction. Oops. Caught the edge of the screen there, and it did not like that. So the same picture here over and over and over again, but just shifting in the x direction, right? So, okay, we could even go backwards in this x direction, stuff like this. And if you kind of put all of these together, it kind of almost looks like, I don't know, like a thing of ribs or something. So you get something that looks like this here. I'll shade them different colors. Just kind of the outside and the inside of this here. All right, so this right here, in words as best as possible, right, trying to describe this thing. Well, I would say that this is a parabola, and I'll say it's shifted freely in the x direction. It's a little bit better than, you know, just like a plate of ribs, I suppose. So yes, equations like this that are missing a variable are quite nice. Right? And they'll get a special name in section 6 here in chapter 12. And they'll continue to come up kind of all throughout the course. But we will give these things a special name and whatnot, and claim as we are not done with these types of surfaces. All right, that's it for me and for this video. Thank you very much for watching. I'll see you guys next time.